All right, here we go. Wednesday. Go ahead and get out your homework. All right, let's see. It was 1 through 16 all. So Pythagorean theorem, review of last year's material. Here we go. Number 1 is 26. Notice they don't have units here. Number 2 is 13. Number 3 is 9.43. They did say round to the nearest hundredth. Number 4, 15.81. Number 5, 11.31. Number 6, 17.89. Number 7 is 20. Number 8, 12.96. Number 9, 39.55. Number 10, 6.24. 11 is yes. 12 is no. 13 is yes. 14 is no. 15 is yes. And 16 is no. And there you go. Go ahead and answer question number 1 on the Google form. All right, let's take a look at the calendar. Once again, we got 2 weeks. I'm not doing a Chapter 11 test. I'm not going to cover all of Chapter 12, which is the last chapter in the book, but I will cover 2 of the sections, the 2 most important ones. It's basically the quadratic formula, or the quadratic equation, or I should say using the quadratic formula to solve quadratic equations. Okay, and then the second to the last week there looks like we end on a final on Friday. That will be your English final. The following week, remember, we have that Monday off for the holiday, so 3-day weekend. And the schedule goes, let's see, Tuesday is science, Wednesday is Latin, Thursday will be your math test, and Friday will be your history test. And that will be the schedule for that final week. Just be a word of caution here. Remember, we're going to, that third week there, we're going to take 2 days to review, and then you're not going to take your math final until Thursday of that following week. So make sure you keep the material handy, and obviously, if you have any questions, make sure you send me an email. All right, here's your homework for tonight. All right. Well, we're going to do another application dealing with square roots, right? This is called multiplying and dividing radicals. Now, in pre-algebra, you did learn how to multiply with radicals. You did not learn how to divide, however. So some of this might be a little bit of a review, but we will combine it with what we've learned with the simplification process. Last year, you didn't know about the simplification process. All right, so basically, just can you multiply or divide with radical expressions? Radical expression is how we describe multiplying, dividing, adding, subtracting with square root symbols. This year, we only focus on square roots. As we go into Algebra 2 and higher, you'll see cube roots and higher roots. All right, this is both easy and hard. Easy in the sense the rule is pretty basic. It's easy to understand the basic rule. It's a little bit challenging because of the simplification process. It can get a little messy. All right, you need to write this down. So we'll do multiplying first and then dividing second. Well, we have a rule for multiplying radicals. Here's how it works. If you have similar radicals, meaning a square root times a square root, a cube root times a square root, we're going to hold that. I'm going to leave that question until Algebra 2 in pre-calculus. But for this year, square root times a square root. If you have a square root times a square root with coefficients a and c, notice I got a times root b times c times root d. If that is the case, then in simplification instructions, we multiply the outside with the outside and the inside with the inside. All right, and here's what I mean. So let's say the outside would be a and c, that's the blue part. The inside would be the b and the d. So when it says multiply the outside with the outside and the inside with the inside, that's literally what it means to do. So we multiply a times c, we'll put a big long square root symbol, we multiply b times d. That's the easy part, right? That's not challenging at all. The challenging part ends up being the simplification process. Remember, we now no longer leave the square root of 40 as the square root of 40. We simplify it. All right, so the simplification can take a few steps. Remember, you can do it in one big step if you can figure out what's the largest perfect square that goes into what's underneath the radical symbol. However, if you can't figure that out, it may take you 2 or even 3 steps to do this. Okay, so let me show you an example. All right, so we have 3 root 2 times 4 root 18. All right, so you're allowed to do this as long as you're multiplying a square root times a square root this year. All right, and oh, by the way, they're not going to trick you and have you multiply a square root times a cube root. All right, so let's see how this is done. So I told you the rule basically was outside with outside, inside with inside. So let's do that. Blue times blue, red times red. All right, just don't forget the radical symbol there. All right, so that would be what? 3 times 4, big long square root symbols, 2 times 18. Makes sense? All right, so the simplification process, 3 times 4 is 12, 2 times 18 is 13. The simplification process says the following. Well, the 12, there's nothing to simplify there, but the 36, it's underneath the radical symbol. So is there a perfect square that goes into 36? And well, like 36 is a perfect square. So in other words, we could write 36 as 6 squared. I would not recommend writing it this way. I'm just showing you this. And remember, square root cancels squaring. So this is really 12 times 6, which is 72. Okay, so that's recall the simplification process. So that's pretty easy when it was a perfect square, but it won't always be a perfect square. Okay, here's another example. Outsides with outside, inside with inside. Well, the 2 is the coefficient of root 5. What's the coefficient of root 7? Well, there's no number there. Remember, we can always have a 1 there. 1 times root 7 is still root 7. So this is really outside 2 times 1, square root symbol 5 times 7. Makes sense? Okay, 2 times 1 is 2. 5 times 7 is 35. Is there any perfect square that goes into 35? No, so that is your answer. In math terms, we call this the exact answer, right? Because remember, if we grab our calculator and we do 2 times the square root of 35, we don't get an exact answer. Your calculator rounds because remember, square root of 35 is an irrational number. Well, I mean, we get approximately 11.8. Tonight for homework, we're only doing the exact answers. There's no calculator that is necessary to get to an answer. Calculator might help you see what perfect square goes in the number, but I don't want you to do 2 times the square root of 35. 2 times the square root of 35 is the answer. Okay? So all we have now is do a bunch of examples. All right, let's see how this works. All right, the one on the left there. So 2 root 10 times 3 root 20. All right, so outside with outside, inside with inside. So that would be 2 times 3, square root symbol 10 times 20. You catching on? Okay, 2 times 3 is 6. 10 times 20 is 200. Okay? All right, now we have to do the simplification step. What is the largest perfect square that goes into 200? Well, hopefully you realize that it's 100. A 200 can be written as 100 times 2. And I know what the square root of 100 is. The square root of 100 is 10. Multiply that 10 times 6. 10 times 6 is 60. So we get 60 root 2. Now, I'm not skipping a step. I'm certainly skipping some notation, and this is common. But just remember, where did that 60 come from? It came from the fact that the square root of 100 is 10. So I'm pulling a 10 out from underneath the radical symbol. In other words, I'm taking the square root of 100. Okay, can't take the square root of 2. It's irrational. We would get an approximate answer. But 60 root 2 is the exact answer. So that's what homework will look like tonight. If you didn't realize that 100 goes into 200 and maybe you saw that 4 goes into 200, that's cool. But you simply would have a couple extra steps. All right, let's do the next one. So root 3 times root 3 times root 4. So the rule says outsides with outside, inside with insides. Well, the outside would be 1 times 1 times 1, which is just 1. And the inside would be 3 times 3 times 4. 3 times 3 is 9. 9 times 4 is 36. And I know what the square root of 36 is. The square root of 36 is 6. So that one's a little easy, right? The more challenging ones are like the ones on the left. So let's do some more of those. All right, so 2 more examples. 5 root 3 times 2 root 3. The first one on the left there. All right, outside with outside, inside with inside. 5 times 2 is 10. 3 times 3 is 9. Square root of 9 is 3, and 3 times 10 is 30. All right, that worked pretty easy. How about the next one? Let's see, outsides would be 1. 1 times 1 is 1. Insides, 11 times 44 is a very large number. Okay, one thing that you can do, you don't have to do this. You can multiply 11 times 44, but then you got to figure out what perfect square goes into it. Before you do that step, however, we can simplify, well, not square root of 11, but we could simplify 44, right? Well, I can see what goes into 40, what perfect square goes into 44. Well, 4 does. So before I do that initial multiplication, I could simplify one of those square roots. I don't have to, but it would certainly make my life a little bit easier. Square root of 4 is 2, so this turns into, watch what I do here, the square root of 11 times 2 root 11. All I did was simplify the square root of 44 into 2 root 11. Why did I do that instead of multiplying? Well, now I'm multiplying with smaller numbers, okay? Coefficients with coefficients, outsides with outsides, insides with insides. Now I have 1 times 2, and 11 times 11. Well, 11 times 11 is 121. Or you realize that 11 times 11 is 11 squared. The square root of 11 squared is 11. So is the square root of 121. So the square root of 121 is 11, and 11 times 2 is 22. All right, for those of you that need to replay that again. But in reality, that's how you do multiplication. It's not much more complicated than that. Okay. So on to it's not the more challenging one, but it has more rules. All right, division. So we're going to talk about not the rules of division, but the rules in general of doing operations with radicals. So these are 3 rules, not for division, but for rules for operating with radicals. Meaning, like, what do you do when you add, subtract, multiply, and divide? Not how to do those 3 things, but some overarching rules that apply. There's 3 of them. All right, I need you to write these down. These are really critical. We're going to use them a lot in geometry. All right, there are 3 rules for dealing with radicals. In other words, how do you put radicals in simplest form? All right, first off, and this is what we've been doing, there are no perfect squares that are allowed to be under the radical, meaning you can't have a 9 or 4 or a 16 underneath the radical. You have to take that square root. The second rule, this is the one that's more challenging. We cannot have any fractions underneath the radical, right? And you're like, well, I've seen fractions before. Right, you are, but we just don't leave them as fractions. So no fractions are allowed underneath the square root symbol. And the last one, the one that is the bane of most math students, is that there are no radicals, meaning no square root symbols, allowed in the denominator of a fraction. You're like, well, didn't you just say there were no fractions allowed? I said that. Rule 2 and 3 are a little bit complicated. I need to show you some examples. But Rule 2 says you can't have any fractions underneath the radical symbol, the square root symbol. And Rule 3 says, well, if you have a fraction, you can't have a square root symbol in the denominator. So what does all that mean? Let's look at an example of each one. Well, the first one we've already seen. I mean, this is what we've been doing, right? The square root of 44 says there's no perfect squares underneath the radical. Is there a perfect square in 44? Sure is. 4 times 11, right? So we take the square root of 4, which is 2, and we get 2 root 11. Now notice there are no more perfect squares underneath the square root symbol. There's just 11. Okay, if there was a 9, we'd take the square root of 9. All right, so that's the rule that we've been operating under so far. But there's 2 more of those rules, the more complicated ones. The other 2 are no fractions in the radical, right? And there can be no radicals in the denominator of a fraction. They kind of seem like they would contradict each other. Let me show you what this means. So the rule number 2, it looks like this. If I have a square root symbol, I can have no fraction underneath the symbol. See what I have right there, the square root of 3/7. I have a fraction inside or underneath the radical symbol. That is not allowed. Okay? That doesn't mean that it's bad math. It's just simply we don't leave it in that form. We have to change it. So today's class is, well, what do we do if that's the case? The second one, or I should say the third one there, is that if I have a fraction, I cannot have a square root in the denominator. Notice the difference between 2 and 3. In 2, I have the entire fraction underneath the square root symbol. In number 3, I don't have the entire fraction underneath the square root symbol. I just have the denominator. Neither 2 or neither 3 is allowed. It doesn't mean that you've divided by 0 or you've done 9 plus 2 and got 13. It's not that kind of bad math. It's just that we do not leave item number 2 or item number 3 like that as our final answer. We may get 2 or 3, right? Number 2 or number 3 there. We may get that in the process of multiplying or dividing. We just do not leave the answer looking as the way it does right now in number 2 or 3. Now, this is the first time you've heard this, right? You're being exposed to this. In geometry, you're going to get exposed to this frequently, and you'll become professionals of dealing with this. You won't even think about it by the end of geometry, but for right now, this is kind of weird and new. So let's just do a whole bunch of examples. All right, so we already know how to handle question number 1, and we'll do that throughout this process. It's just rule number 1. It's rule number 2 and number 3 that we have to deal with. So let's do some rule number 2s first. Rule number 2 says you cannot have a square root or a fraction underneath the square root symbol. At the end, like your final answer, cannot. Notice the start here. I do, in fact, have 2 fractions underneath the square root symbol. It's fine to start with. You just can't end up. It can't be your final answer. So how do we do this? Well, our previous rule says outsides with outsides, inside with insides. Well, I got 1 as the outside number, so that's taken care of. So we just multiply the insides. So let's multiply the insides. All right, pro tip to you is that if you're multiplying with fractions, cross-reduce first if you can. Notice I got 3 sevenths times 14 27, so I can do some cross-reduction. 3 goes into 3 once, 3 goes into 27, 9 times? 7 goes into 7 once, 7 goes into 14 twice. So 1 times 2 is 2, 1 times 9 is 9, I get 2/9. Now, we saw this last year in pre-algebra, and what we said was the following. We said that you can break this up into the square root of 2, the numerator, over the square root of 9, the denominator. You're allowed to do that. Well, I know what the square root of 9 is. The square root of 9 is 3. Now, notice, I do have a fraction, but it's not underneath the entire square root symbol. Okay, so this is allowed. Rule 3 says that we're not allowed to have a square root symbol in the denominator, and I don't in this case, so life is good. So, to back up, this is rule 2, no fractions in the radical. So the square root symbol does not contain a fraction. It contains, in this case, for the final answer, a 2, which is allowed. Okay, no perfect squares. We've met rule number 1. We've met rule number 2. Rule number 3 doesn't apply here because the denominator is 3. All right, so this one can be confusing for a lot of students at first. You're like, well, when am I allowed, when I'm not? So the basic rule is this. Look at your final answer, the one there in yellow, and make sure that it meets all 3 of those rules. No perfect squares. The square root of 2 is not a perfect square. No fractions in the radical. The only radical there is the square root of 2, and 2 is 2. It's not a fraction. And then the last one, you can have, if you have a fraction, you can have no square roots in the denominator. The denominator here is 3, so I'm good to go. All right, let's do one. All right, let's see, outsides with outside, inside with inside. So for me, right, remember you can't multiply mixed numbers. You have to change them to improper fractions first. 3 times 7, 21, plus 3 is 24. 2 times 3 is 6, plus 1 is 7. So those are the 2 fractions that I get once I convert the mixed numbers to improper fractions. We good? Okay, then we multiply. Can we do any cross reduction? Sure can. Let's see, 3 goes into 24, 8 times? 3 goes into 3 once, and then the 7s would cancel. So I'm just left with what? The square root of 8 over 1. Okay? Which would turn into the square root of 8 over the square root of 1. I know what the square root of 1 is. The square root of 1 is 1. Any number divided by 1 is just itself. Now, rule number 1 says you can't have any perfect squares underneath the square root symbol. Is there any perfect square that goes into 8? Sure, 4. 4 times 2 is 8, and the square root of 4 is 2, so we're left with 2 root 2. All right, notice how long it took us to get an answer there. All right, this has a lot of steps. So let's make sure we haven't violated anything of our 3 rules. No perfect squares underneath the radical. The only number I have underneath the radical is 2. And square root of 2 is not perfect square. We have no fractions, so that didn't violate 2 or 3 for the final answer. Notice, we violated 2 and 3 throughout the problem. It's just the final answer. These are rules for simplification. The final answer that must meet all the rules there for 1, 2, and 3. Starting to make sense? Okay, let's do it. All right, really ugly numbers here, large numbers. So when you do the multiplication, I would certainly, if you can, cross reduce. 8, well, luckily for us, yeah, they kind of make these problems so that you can do some cross reductions here. So 8 goes into 8 once, 8 goes into 32 4 times, 11 goes into 11 once, and 11 goes into 22 twice. So we get what? The square root of 2 fourths. Okay, so technically right now we're in violation of rule number 2, right? No fractions, but as soon as we see if we can simplify this, the square root of 2 over the square root of 4, we see that the square root of 4 is 2. So we get root 2 over 2, and let's see, we're good for rule 1, we're good for rule 2, and we're good for rule 3. So we know we fully simplified. Okay? All right. So what does rule 3 mean? No radicals in the denominator. This is the one that causes students the most hassle. It's a pretty easy rule to remember if you pay attention, so really pay attention. But most students complain about this rule, and I was with you when I first learned this. It seems like a silly rule, and my teacher, did a pretty poor job of explaining, well, why is this a rule? I kind of understand rule 1, and I certainly understand. I'm sorry, I certainly understand rule 1. I kind of understand rule 2, right? But why rule 3? And the true reason of rule 3 is that if you follow it, you will find, especially when we get to higher level math, algebra 2 through calculus, you will find that more things will be able to be simplified or canceled if you follow rule 3. And I shouldn't say if you follow, you must follow rule 3. Okay? So rule 3 is kind of like the reducing fractions. Why do you reduce a fraction? Isn't 2 fourths a fine fraction? Why do we have to turn 2 fourths into 1/2? That's never explained really well either. And the true reason is it makes the math a little bit easier. And so I'm going to claim, I won't show you this year certainly, but I'm going to claim that following rule 3 will make the math a little bit easier as you go upwards in math. Now you're going to see in this process, it certainly doesn't make the math, at least for this year in Algebra 1, any easier. It's extra work. But you will find later on that when you do this process, that it will make the follow-on math a whole lot easier. But you won't see that until Algebra 2. All right, so this is what it looks like. This is what's not allowed, right? I cannot have a square root as a final answer in the denominator. I can have it in the numerator, the previous couple of answers we did, but I'm not allowed to have the square root in the denominator. So what's making this bad is that square root of 5. So we're going to use a math trick, right? Here's a math trick, and you've used this math trick before, by the way. The math trick says this: we can multiply any fraction times 1 and nothing changes. If you take 2 over root 5 and multiply by 1, you're left with 2 over root 5. I've changed nothing. So I am allowed to multiply the fraction times 1. I'm going to write 1 as a fraction, 1 over 1. That's still 1. I'm going to multiply that fraction times 1. The only difference is that 1 will not look like 1. It will be the mathematical value of 1. I'm going to write 1 over 1 as root 5 over root 5. What's the square root of 5 divided by the square root of 5? It's 1. So that's really 1. So I'm multiplying by 1, but watch what happens when I multiply straight across. 2 times root 5 is 2 root 5. The square root of 5 times the square root of 5 is the square root of 25. The square root of 25 is 5. Notice I don't have a square root symbol in the denominator. I have one in the numerator, and that's fine. Most students at this point raise their hand and say, well, that doesn't look any more simplified than the first one, right? In fact, it looks more complicated, and I would agree, right? And you will find out later, as I said, that this actually will make the follow-on math, what we would do with this, we will not see that this year, what we do with this a whole lot easier. So you're going to have to trust me on this. So why did I choose to multiply the top and the bottom by the square root of 5? So the technique is this. Because you're trying to get rid of the square root symbol in the denominator, always, when you have a square root symbol in the denominator, always multiply the fraction times the denominator's radical expression. In other words, the square root of 5. If it was the square root of 3, we'd multiply by the square root of 3. If it's a square root of 17, we'd multiply by top and bottom by the square root of 17. Okay? Let's see that again. All right, so we have the square root of 7/8. All right, let's do another one. All right, two fractions, we're going to multiply, so that's pretty easy. Let's see, 10 times 1 and 13 times 2. I can do some cross reduction first. 2 goes into 2 once, 2 goes into 10 5 times. So 5 times 1 is 5, and 13 times 1 is 13. Okay, so what? This could be broken down into what? The square root of 5 over the square root of 13. Square root of 5 is fine. No violations there. There's no perfect squares. There's also no perfect squares in the square root of 13, so that one's good. But we have a square root symbol in the denominator, not allowed. So we're going to multiply the top and the bottom, the numerator and the denominator, by root 13. Why not root 5? Well, root 5 isn't the one that's giving us our problem. It's the square root of 13 that's giving us the problem. So we multiply top and bottom by the square root of 13. You catching on? Okay, so let's see. 5 times 13, well, that's 65. 13 times 13 is what? 169, and the square root of 169 is 30. It works this way every single time, right? All right. Well, there you go. What you need one more? All right, we'll do one more. One more. All right, this is probably as complicated as it gets tonight for homework. Okay. All right, so we got 5 root 2 over the square root of 35. Any perfect squares, top or bottom? Numerator, denominator? Nope. Okay, so what's giving us the problem here? All right, what's giving us the problem is that square root of 35. So we're going to what? Multiply the top and bottom, right? The top and bottom by the square root of 35. Why not the square root of 2? Because square root of 2 is fine, right? It's the square root of 35. And just remember, the square root of 35 over the square root of 35 is the number 1. So I'm really multiplying the fraction times 1. I'm not changing anything. All right, so let's see. Outsides with outside, insides with inside. So 5 times 1 is 5, obviously. And then 2 times 35 is what? 70? Okay. And the square root of 35 times the square root of 35 is, well, 35 squared, and the square root of 35 squared is 35. Make sure you understand where I got those numbers from. Okay? Further, now take a look at that. What do you notice? Any perfect squares in 70? No, but look, we got a fraction, 5 over 35. 5 over 30. Hey, that could be reduced, right? Right? What is 5 over 35 reduced to? 1/7, right? So 1 times root 70 over 7, and I can just write that as square root of 70 over 7. Is that starting to make sense? Now, I certainly can't do 400 of these, right? And I've only done a selected number of these. Probably some of you need a little bit more practice on this. So that's why tonight for homework you have 2 through 26 evens. Give it a shot. If you run into any problems, it's Monday, or I'm sorry, it's Wednesday. If you run into any problems, send me an email. I'll give you a quick hint on what to do to solve that one. I'd rather you get the answer while you're trying to do the work than to wait until 2 days to try to get the answers. Make sense? All right. Good luck on your homework. Send me an email if you need any help, and that'll do it for Wednesday. See you guys on Friday.